Our 10 questions on resistance in circuits. We're going to think a little bit about Kirchhoff's laws, combining resistors in series and parallel, and various other concepts. So let's get started. First of all, we've got our voltmeter connected across a 50 kilo ohm resistor, and it's in series with a 100 kilo ohm resistor as well. You should be aware that this is a version of the potential divider. So what we can do here is very simply take our resistance. I'm going to call it R1. That's the 50 kilo ohms, and I'm going to divide R1 by the sum of the two resistors, and I'm going to multiply it by this epsilon, which is the EMF. So in that case, we're dividing the potentials, showing that they're in proportion to the resistance and the total. So we've simply got 5 volts there, multiplied by 50, divided by 50 plus 100. Okay, and if we put in the maths, that's 1/3 of 5, which comes out around 1.67, so we'll call that 1.7, and so therefore our answer here is B. Okay, key point here being that potential dividers do exactly what the name suggests, in that they will divide the potential, and the potential will be divided according to the resistances. The greater the resistance, or the greater the proportion of the resistance, then the more voltage will be taken up. Number 2, we've got a resistor network, and we know the potential difference. We want to find out the current in the 5 ohm resistor, and this is where we're going to use our Kirchhoff's laws. Now, Kirchhoff's laws tell us a couple of things. One, that in series, our currents add up. Why is that important here? Well, we can see that the 5 ohm and the 3 ohm resistor are connected in series, and so therefore they're actually going to have the same current running through them. So what I should really be doing here is calculating the total resistance of those two guys there. I don't need to worry about the 3 and the 1. I need to worry about the 5 and the 3 in the bottom. Because remember, when we're calculating total resistance, we're really replacing the two individual resistors with one big resistance. And we know that the current between within those two resistors is going to be the same. So I'm going to do that here. Okay, I'm going to think about the fact that my I is equal to V over R. Okay, my total resistance here is 5 plus 3 equals to 8. And my V is also 8. Now, why is that? Well, the potential difference is 8. And when we're using Kirchhoff's second law, we should be aware that it doesn't really matter which direction, which part of the loop we're looking at, the top loop or the bottom loop, both of those branches have the same potential difference. So because we are both ways of connecting up the 2 points X and Y, so therefore they must have the same potential difference, i.e. 8 volts. We've got 8 divided by 8, which leaves me with 1 amp, and so therefore my answer here is A, 1 amp, using the fact that the currents in there, my 5 and my 3, are going to be the same. Now, there's obviously a much more complicated way of doing that. That's where I started off with this, but really you don't need to worry about the 3 and the 1 ohm there. You just need to worry about the information you're given on that bottom branch. I hope that's clear. This is one that requires a bit of thinking. Okay, we've got a resistance of component X which decreases when the intensity increases. That is most likely going to be an LDR. Okay, that's exactly how our negative coefficient LDRs work. Intensity up and resistance down. Let's think about how that works. Well, firstly, let's just underline that, okay? That is the really important bit, because we're going to increase the intensity here. Well, let's work it through. If we increase the intensity, the resistance decreases. That's the information we're given in the first place. As the resistance decreases, the current is therefore going to increase. We've got two resistances in series here, and so therefore, as one goes down, the sum is going to go down. We've got two values there which are adding together. Now let's think about the potential. So we can start crossing off a couple of answers here. We know that the current should increase, all right? So I've got a couple A and B there, which are potential answers. Now we need to switch our attention to that fixed resistor. We know that the fixed resistor has a fixed resistance, and so therefore we're saying here current is going up, its resistance is constant, and therefore the potential across the fixed resistor is going to increase. Okay, and that's because of V equal to IR. We've got R remaining the same, I going up, and therefore V going up. Now, why is that important? Well, we're using our energy conservation, i.e. Kirchhoff's second law here, says that the numbers must add up to be the same amount. If the EMF was 5, say, then the totals must also be 5. If we're having the potential of R going up, that therefore means that the potential across X is going down. Okay, and I've written K2 there. That is Kirchhoff's second law. In other words, the ammeter reading increases and the voltmeter reading is going to decrease. I think it's a really good idea sometimes to use equations and sometimes just use simple words to work through these equations, these situations, and this is definitely one of those. Okay, great question, this one. Okay, I've taken the question and I've added a few things here. Notice here that I've added a couple of pluses and minuses, and this is really to hammer home the point here that we are dealing with a quite complicated situation here. If you look at the long side of my batteries, okay, that is the positive terminal. So anything that is connected to that positive terminal becomes positive itself, all right? And the reason we're doing that is because the top of my 3 ohm resistor is essentially going to become positive with respect to the bottom. That's because it's connected to the positive terminal of the battery. And that's important for a little bit later we think about our Kirchhoff's laws. Okay, now let's think about our loop here, our red one. If the ammeter reading is 0, that must mean that no current is flowing there, and that must also mean that the current in the 3 ohm resistor is equal to the current in the 9 ohm resistor. This is therefore a potential divider. So what we can do then is we can use our potential divider formula. Again, V equal to epsilon, the EMF, times R1 plus R2, times R1, sorry, divided by R1, R2. In this case, we're dealing with the EMF in that red loop. That's the 24 volts. So we can do a bit of multiplication, and we're left with the fact that the potential difference for this to happen must be 6. Okay, now you can see that that is one of our answers there. Okay, in fact, it is the answer here, B, but why? We notice here we've got 2 positive terminals connected to one another. This is just the same as if we had 2 batteries connected in opposition to one another. The current will only be 0 if the 2 batteries have the same EMF. In other words, the current here will only be equal to 0 if my EMF at P is equal to the potential difference across that 3 ohm resistor. We've just calculated the potential difference is 3, and so therefore P must also have a value of 6 volts. Okay, so within this loop, if we use Kirchhoff's laws, then we're going to find that those 2 values will cancel each other out, and so therefore we're looking at B, 6 volts. Now we've got a kind of favourite combination here of IB. You'll notice that this combination comes up quite a few times. We'll see it again later. We've got, we want to calculate the reading on the voltmeter. And that is, this is very similar to our internal resistance problem. Because we're connecting across a EMF with a resistance connected in series. So you can kind of imagine this cropping up in an internal resistance question too. Let's firstly start off with that little red loop. We've got 2 resistors. Now I'm going to assume that everyone's happy when we connect 2 resistors in parallel. Those resistors, their total resistance will reduce. In fact, when they're identical, the total resistance of 2 resistors connected in parallel with identical resistance is simply half of their value. So therefore, if we've got 6 and a 6, it's going to make a resistance of 3. That 3 ohm resistance is therefore connected in series with a 1 ohm resistance, and so therefore my resistance in total becomes 1 plus 3, 4 ohms. Why am I doing that? Well, as is common, what we like to do is we like to calculate the current in these situations. Therefore, I've got 12 volt EMF divided by the 4 ohm resistance, that's 3 amps. I've got 3 amps working out there. I can then, if you like, calculate the lost volts here, the voltage across that little resistor, which is 1 ohm. And so therefore that's V equal to IR, and that's just 3 times 1, which is 3 volts. So 3 volts are lost, okay, meaning that the potential difference that we measure there is going to be my EMF take away my potential difference across the small resistor, which is small v, which is 12 minus 3, which is 9 volts. And so therefore our answer here is D. Notice here I'm referring this to be similar to an ideal to our internal resistance question. It's not stated as an internal resistance, however the thinking is exactly the same. Okay, here we've got Kirchhoff's laws, and this is one which kind of tests your understanding of directions. Okay, first things first, I think it's worth our while looking at the loop here. Now, in this, in our picture here, it's worth stating that we've got three potential differences. We've got the potential difference across R1, which is just I1, R1. We've got the potential across R2 and R3, and they've got the similar form I2, R2, and I3, R3. Now, I've deliberately put a positive sign there. Why is that? Well, if we follow our loop, and I'll just get my cursor right here, when I follow my loop round, I am following the current. And that means I have no minus signs when I'm adding together my potential differences. Remember, if you're going against the current, then the current effectively becomes negative. And so therefore, we've got a bunch of positive potential differences to add into our loop. Okay, so we're going to use Kirchhoff's second law here to do the first part, which is simply the sum of the EMFs is equal to the sum of the potentials. Now, what I'm expecting is all of those potentials to add up, and I only need to worry about two of them. I've got I1, R1, and I3, R3. But then I also need to think about the EMFs, and this is where we have to be careful. You notice we are coming out of the negative terminal and back into the positive terminal of the EMF. Actually, this becomes a negative EMF according to our rules. And so therefore, we're left with minus E is equal to I1, R1 plus I3, R3. Okay, just looking at the options there, we've got a couple of potential options there. It's then worth thinking about the difference between option A and B, and we've got to look at junction Y. You can see here we've got a current going in, which is I1, and two currents coming out, I2 and I3. It's clear that I1 must split up into I2 and I3, meaning therefore that my answer here is A. I1 is equal to I2 plus I3. If you're not clear about the rules on using Kirchhoff's second law, I do have a video on that in terms of directions and what happens to EMFs in that case, and I'd encourage you to have a look at that. I'll try and find a link to that and include in the bio. All right, I think this is the one that students have reported as finding hardest, so we'll try and take it slowly, but not too slowly, I hope. I do have a limit on these videos. Okay, 4 identical resistors, each of in turn of resistance R. Okay, we've got a couple of resistances there. They're going to add together to make 2R. We've then got those 2Rs connected in parallel with another resistance right there. Okay, so these guys are connected in a slightly complicated way, and we're going to have to calculate their total resistance. We want to know the current in resistor X. That's our key point here. So, oops, we've got the wrong one there. Okay, let's have a look there. I'm going to call the resistance in blue RA. There is a resistor there with resistance R, that's our resistance X. It's got the resistance value R. And we've got 2R there, okay? And so therefore, our total resistance A is going to be, we add together in parallel, 2/3 of R. Okay, we now take our value from above and add it together with that final resistance, which is connected in series there, which is just an individual resistor of resistance R. 5/3R is our total. 1 plus 2/3 is going to give 5/3. Okay, so hopefully you can see there, our total resistance here is 5/3 of the individual resistance values R. What we're saying here is we're replacing all 4 of these resistors with one resistance which has the value of 5/3R. Why do we do this? Well, we can do this to calculate our current through the whole circuit. We do that by using our I equal to V over R. This time we're going to use the total resistance, which we've just calculated as 5/3R. We've got EMF divided by 5/3R. We've got 5/3 on the bottom, so it becomes a 3/5 on the top there. Okay, so this is the current which is drawn from the battery. Okay, this is the current that is effectively drawn by all of these resistors working together. What we need to now do is say what happens to that resistance, to that current as it flows around the circuit. Well, obviously, that's the current that flows through my first resistor as it goes around the circuit, but it then is going to split up across the 2 parallel branches. Now, 2 parallel branches have different resistances, and therefore they're going to split up in a different ratio, and that's where you have to identify that red resistance is double the resistance of our resistance value X. Put more simply, okay, I is split into a 2-to-1 ratio. And because X has got the lower resistance, it's going to have the higher current. X has got half of the value of the resistance in the red branch, and therefore it's going to have double the current. So what we need to take is my 3 epsilon over 5R and split it up into a 2-to-1 ratio. Now hopefully you can see that I've got 3 multiplier there. Well, that means that 2 epsilon over 5R is going to flow through resistor X because it has half the resistance, and therefore 1 epsilon over 5R is going to flow through the red resistors there that I've highlighted. Noticing there that we've got 2 going through X and 1 going through the red. 2 plus 1 is our 3 times epsilon over 5R. Very complicated problem, this one. It's really worth your time, taking a bit of time to set up the resistances so that you can really understand what's going on here. Slightly less complicated this time. We want to calculate the resistance of these 3 guys, and they're connected in a slightly different way. Now, this is really just an issue of identifying what's in series with what. You should be able to see that the 2 3 ohm resistors are in series with one another, and so therefore they would add up to make a total resistance of 6. We're then going to add our 2 ohm resistor, which is in parallel with those guys, and we're going to find our total resistance. And so therefore, our total resistance is 1 over RT, is 1 over 3 plus 3, plus 1 over 2. Okay, therefore we've got 1 over RT is going to come up as 1 over 6 plus 1 over 2, which is 4 over 6. I then need to remember to flip this, giving me 1.5 ohms. Okay, so don't be confused by the question there. Really what we're just saying is what is the value of the resistance. It's not simply 2, because we have to take into account the effect of all of the other resistors as they're connected in parallel. Second last question then. Again, we've spotted this before. And again, I'm going to assume that everyone's happy that the total resistance of that little bit of the circuit is 3 ohms, because it's 6 divided by 2. Okay, we therefore have a total resistance of 3 plus 3. That's our X plus that 3 ohms is equal to 6. And then to get our current, all we have to do is divide the EMF of our circuit, 6 volts by 6 ohms, which gives me 1 amp. Okay, last one. Here's our Kirchhoff law again. Now, we're going to use Kirchhoff's second law here, and we're going to remember the thing that we just said. If we are going against the current at any time, then our potentials become negative. So we've got potential difference across our, we don't need to worry about I1, okay, because it's not in the loop. We need to worry about our potential 2, if you like, and potential 3. Okay, potential 2 is just 3 ohms times my I2, and potential 3 is just 4 ohms times my I3. Now, you notice here that as we go around our anti-clockwise loop, I am in the same direction as the bottom potential, 4I3, and I'm in the opposite direction of the top potential, 3I2. Therefore, that top potential becomes negative, minus 3I2, and we've got a positive 1 on the bottom. Now, why is there 0 in there? Well, there are no EMFs in my loop. I have not got any batteries here, I've got no cells, and so therefore no EMFs, and therefore all we're dealing with is pure potential differences. Well, there we go. 4I3 is minus 3I2 is equal to 0. I'm aware there's a lot in there, folks. Please take the time to watch this, to pause as you're watching, to compare to your answer, to watch multiple times, and as always, let me know if there's anything you're not clear about. Thanks for watching.